Hi everyone, in this video I'm going to share with you my own perspectives on the mathematical preparation of students for post-secondary school study. In line with the goals of STEM education, this video gives personal perceptions of the nature of post-secondary mathematics and discusses potential obstacles that the students might experience in the post-secondary learning setting. For user of this video, actually, this video does not provide a lecture on the post-secondary math. It simply intends to highlight some persistent mathematical issues that might arise during teaching and learning. For teachers, it can serve as a supplementary reference to any teacher's guide. And hence, pedagogy must be developed to address any mathematical deficiency in the student's understanding. As we all know, there is a lack of consensus of what kind of mathematical content should be taught at schools and colleges, and what kind of assessment to be developed to prepare students for their undergraduate studies in STEM. And as a result, the pen and the paper assessment still largely exist in post-secondary programs. Now, in view of this, the student success in assessments would effectively help build their confidence and sustain their interest in STEM subjects. And hence, the students must be guided to equip themselves with a solid foundation in math, as well as the reasoning skills for independent lifelong learning purposes. The important role played by mathematics in any STEM education is evident in the joint statement made by the National Council of Supervisors of Mathematics (NCSM) and the National Council of Teachers of Mathematics (NCTM) in 2021, that the students need a strong mathematics foundation to succeed in STEM fields and to make sense of the STEM related topics in their daily lives. And in a STEM program, the mathematics and the science play a different role from technology and engineering, in that mathematics and science are essentially school subjects that must be taught well for both comprehensive education and as the foundation for any STEM initiative. The post-secondary schooling experience of most students start with pre-university studies, where mathematics is a compulsory subject to take. The main purpose of the courses are to bridge the gap between the secondary school and the university studies, for ensuring a smooth transition from SPM to a wide range of science-related degrees, such as engineering, bioscience, computer science, etc. The mathematics courses normally cover several areas of mathematics. Students are expected to have completed at least an introductory course in algebra, calculus, and statistics before embarking on their undergraduate studies. In the area of pure math, the distinctive features that distinguish it from the secondary school math is that it includes a deeper analysis of school mathematics and also a heavy focus on the rational and transcendental expressions. There's an explicit reference to the real variables and also the use of intervals. The introduction of several advanced topics, for example, complex numbers, partial fractions, series expansion, implicit differentiation, and differential equations. One of the major concerns is that the students do not seem to engage in learning math as much as in other STEM subjects. And not because the students can't learn or don't like the advanced mathematics, rather they are mainly held back by the lack of conceptual understanding of the elementary content, the mastery of the basic computations, and the reasoning skills, as well as there is the lack of self-efficacy and the curiosity required to explore further. Without adequate interventions, some learning obstacles and misconceptions will last longer than expected. So the rest of this video will be devoted to sharing my experience in dealing with several issues that ought to be addressed as early as possible. First, it is important for students to not only recognize but also to understand what kind of numbers that they are handling in the problem solving context. Now, for the first time, they are told that the real numbers merely consist of two subsets, a set of all the rational numbers and all the irrational numbers, such as the golden ratio, which is the root or a solution of this quadratic equation. Then before introducing complex numbers, however, what might elude the teacher's attention is that the student's interpretation of an idea of what the real number is, or what does it mean by a real number. So to some students, the real numbers are simply equated to the natural numbers or the counting numbers. Why? Because the word real might suggest to them that the number might arise from the nature. That is a matter of a lack of a solid definition of real number, especially in KSSM. One of the evidence to illustrate my point is that the students tend to use an inequality from 3 to less than 7 to mean both a set of all the integers from 3 to less than 7, which are simply 3, 4, 5, and 6, as well as a set of all the real numbers that fall within the same range. The latter is normally expressed in the interval form. Due to this misunderstanding, so whenever they are asked to find the intersection of two real intervals, such as these two, then they somehow erroneously resort to the finite set, where they can find the common elements 5, 6, and 7. Some of the students might be aware that the answer must be in the interval form, and hence they convert back to the interval form from 5 to 7. And this incorrect way of simplifying or concretizing the problem somehow results in the correct answer, although the method is definitely incorrect. Notice that if we change the second interval to between 4 and 10, then by using the floor reasoning, then the students will not get the right answer this time. So one of the issues for teachers' attention is that the question like the first one may not be a good formative assessment questions, as it might mislead students into thinking that they are doing all right with their wrong techniques. Next, students also show their weakness in handling rational numbers and rational expressions. Few students are being aware of the division algorithm for numbers because the KSSM textbook recycles the division with the remainder notation, such as 84 divided by 5, you are going to get a quotient of 16 with the remainder equals 4. And this notation is somehow problematic and also misleading. Let's consider another example where we divide 148 by 9. You're going to get the same quotient 16 and also the same remainder 4. But when the equality sign is concerned, if we assume that this is equal to A, the right hand side is equal to B, and we somehow get C equals B as well in the second row. And eventually it suggests that the A must be equal to C. But this is not the case because we know the two ratios are definitely different quantities. And we can justify this easily by converting the two ratios into the mixed fraction 16 and 4 over 5 and 16 and 4 over 9, where the addend 16 can be cancelled out, leading to this inequality. In KSSM, the division with remainder notation should be replaced by the division algorithm for numbers as early as possible, where the students can see that the statement like this, 84 over 5 is actually equal to 16 plus 4 over 5, where we can multiply both sides by 5, and it simplifies to these equations. That totally makes sense. And the same, it goes to the second example earlier. So in general, if students are given an improper fractions, A over D, or a number A to be divided by a non-zero D, that is the quotient Q and the remainder R, such that A is equal to Q times D plus R, where the remainder, of course, is less than that of divisor. And the benefit of doing so is that it helps prepare the students to learn the polynomial division algorithms or the long divisions at the pre-university level, as well as the modular arithmetic to be learned in a number of courses at the degree level, such as number theory, discrete math, and these courses must be taken by, let's say, the computer science major. Next is the students' misuse of equality sign. Here are two prominent examples that I encounter most frequently. The first one shows the solution given by students when finding the adjoint of matrix A. Now the solution is not properly written here because it violates the definition of equivalent matrices, although it does reveal the correct steps to find the adjoint. Another example has to do with evaluating the indeterminate limit of a rational function here, where this student is expected to cancel out the common factor x minus 1 leads to the 0 over 0 problem. Then before substituting x equals 1 into the reduced fraction here to get the value of 3 over 2. Now in these examples, the equality sign were misused to mean a process or a series of actions to get something to arrive at the answer. So the main difficulty is that the final answer for each of these questions is actually correct. So one of the pedagogical questions to address here is how will the teacher find ways to convince the students to rectify their solutions? The next learning obstacle is that students don't prefer to use the brackets to perform appropriate grouping of terms. For example, when decomposing this rational function into its partial fractions, a student was taught to equate the denominators of the right hand side and then compare the numerators of both sides of the equations. However, some of students fail to apply the bracket to increase the clarity that the ax is indeed multiplied by the entire expression x plus 2. And the same it goes to the term in b. If we substitute x equals 0 into both sides of the first equations, we are supposed to get b equals 2. But substituting x equals 0 into the student equation for x, we will get 4 equals 0 plus 2 plus 0 plus 2 plus 0, which is equal to 4. And hence it doesn't help to solve the problem at all. Evaluating the indeterminate limit is another occasion where the use of bracket is proved to be vital. After performing the conjugation and multiplying the numerators, we are supposed to get 1 minus bracket of x minus 1, which simplifies to 2 minus x. And this enables to cancel out the problematic common factor, 2 minus x. By direct substitution, we will get the right answer 1/2. But for some students, the failure to use the bracket at this juncture might cause them to make unnecessary mistakes. When students learn something by rote, they may not be able to make sense of what they are writing. This includes the confusions of symbols or notation that look alike. For example, students might get confused between the matrix, a 2x2 matrix, and its determinant. The confusion with the same notations with different meanings also happen quite frequently. Here are a few examples where students might mistake one for another. In view of this, teachers must be alert to the student interpretations of the symbols or notation when teaching. In arithmetic, the students were told that the reciprocal of number a, which is 1 over a, is the multiplicative inverse of the number a, which is denoted by a with the power of -1. But later in the studies, they were cautioned not to confuse between the inverse of a function or the inverse of a matrix with their reciprocals. So to understand the distinction, students must be guided to check the identities of each of the mathematical objects. Teachers must be careful in explaining how the solutions of quadratic equations of this form can be obtained. If students are simply taught to take the square root of both sides of these equations to get x, and then adding the plus minus sign on the right, they might see this as a mindless trick that can also be used to answer the corresponding inequality questions, which of course this time results in the wrong answer. Another prominent example is to multiply both sides by the denominator in order to simplify the rational equations. But this doesn't work in general for solving the rational inequality. Students tend to use calculator to find solutions of quadratic equations like this. Although the leading coefficient is negative, it doesn't really affect the answers. But the negative leading coefficient does matter when they solve the corresponding inequality. If the students use the same technique without making sense of what they are doing with their calculator, they might arrive at a wrong answer. The modulus concept is also a source of confusion. Due to rote memorization, the students tend to associate any modulus expressions with the fragmented concept images such as the V-shaped graph, always positive, and replaced with the positive negative sign when solving problems. They actually confuse the input x with the output modulus of x. In precalculus, they learn that the graph of a modulus of a function f of x can be obtained by bending upward the portion of the graph of f below the x-axis. So they sketch the graph of this, and this is the correct answer. But when the students are asked to sketch the graph of a function of modulus of x given the graph of the function f, they might erroneously think that the graph of this function can be obtained by bending to the right, all right, this portion of the graph, or even remove entirely this portion of the graph that lies in the negative x-axis. So these are the wrong answers. To sketch the graph of the function f of modulus of x, what student needs is simply a precise definition of this function consistent with the definition of modulus of x. We know the square root of any positive real number can be positive or negative. But few students come to realize that the square root symbol is actually reserved for the principal or the positive square root. So they're used to thinking that the square root of 9 is actually equal to 3 and -3 instead of simply 3, because of the reasoning with the exponent here. Square root of 9 can be written as square root of positive or -3 holding squared, while the square root can be converted to the rational exponent 1 over 2, where 2 and 1 over 2 cancel out each other. We'll get back positive and -3. But with the calculator, square root of 9 is simply equal to 3. So this creates a conflict for the students to resolve. These confusions actually hinders them in instantaneously knowing why the values of y must be always non-negative when finding the range of the following functions. and sketching the graphs. Students are still largely assessed on how to use elementary skills and knowledge when they are doing calculus questions. For example, when students are asked to differentiate the quotient here, they can find the derivative of the numerator and the denominator, and then plug the functions and their derivatives into the quotient rule formula. But they have no idea how to proceed. And worse, the answer provided are normally in the most simplified form like this. So in order to get this answer, students are expected to be very good at handling rational expressions and the rational exponent. On the other hand, simplifying expression by dividing out any common factor cannot be done without being able to justify why the simplification is legit. So unlike arithmetic, we know the two fractions are actually equivalent, as we may cancel out the common factor 24 from the denominator and the numerator. But when we cancel out the common factor x minus 2 in a rational function like this, we will obtain a simplified function x plus 2, whose domain is definitely different from the original function. When solving equations, students also tend to simplify the problem by dividing out as many factors as possible. This leads to the next issue concerning division by zero. The students must understand why division by zero does not make sense and hence must be avoided when solving equations or finding the domain of rational functions. So there are two cases where we divide a non-zero number a by 0 or dividing 0 by 0. Both are simply undefined. You can find the parallel of division by 0 in solving a system of linear equations when using the inverse matrix method. We know the solution x is not unique when the determinant of a is equal to 0. So to make sense of this, we multiply both sides by determinant of a in these equations, and then substitute 0 for determinant of a. So by scalar multiplications, the left-hand side must now be a null matrix, while on the right-hand side, it will depend on the outcomes of the matrix product, adjoint of a times b. If the product is not a null matrix, so it is a false statement and hence the system has no solution at all. If the product happens to be a null matrix, then x can be any solution. As a conclusion, if we are to better mathematically prepare our students for their undergraduate study in STEM, it requires a collective instead of individual effort to rethink the mathematics education and to address the potential teaching and learning issues that might hinder their progress. While my sharing is by no means exhaustive, so the contribution of ideas and comments from all parties, which include teachers, students, parents, textbook writers, and even policymakers, are always welcome to prompt further discussion on the teaching and learning matters. So from the teacher's perspective, there is the need to rethink the learning progressions so as to provide a coherent framework and to establish connection among topics to enable students to absorb and make sense of the idea discussed. Incorporate reasoning into our lesson might appear more difficult than it seems due to many factors such as cultural resistance or the student's readiness. It might even take years for you to find a suitable level of reasoning to be infused into your own classroom. From my viewpoint, a successful math educator should always show patience in understanding students and respect their thinking. Besides having courage to conduct experimental teaching and make constant reflections on the existing teaching and learning practices.